Okay, I'm going to get out of your way. So folks, you can interrupt Ehsan at any moment. It's all yours, man.
Okay, thank you so much. First of all, thank you so much for giving me this opportunity to first introduce myself, actually, and then talk about quantum information, which was one of the things that I was fascinated by since I was not a kid. I'm not gonna lie, because when I was a kid, I was doing so many other things other than quantum. Since I started my bachelor degree. So as I mentioned before, I come from Iran. I did my bachelor and master back in Iran. When I moved to Canada, like I was 28 years old, I started a PhD program. And I'm not gonna lie, it was, I think like till today, that was the hardest thing I've ever done in my life, apart from the immigration to a new country, which is always hard. Like the story behind the PhD was that I started the whole PhD with quantum biology. So I spent the first 2 years writing up my proposal. I defended my candidacy proposal on quantum biology. And in the third year, I realized that that problem that I chose to solve is not tractable given the device that we had at that time. So I can assume that you guys can guess that it's pretty much late. Like you are toward the end of the third year and that you're realizing that, okay, nice. So whatever you've been working on and you pass your candidacy exam, you convince people that, yes, you can finish this on time in 4 years, 5 years, then you can do that. Then after that, I decided to quit the program. And the morning of that, in the morning of that day, I was sitting in the kitchen back in University of Calgary. And there was a postdoc, his name, but I'm mentioning his name because he saved my, I would say my career, my life, sort of. I was sitting in the kitchen and then there was a postdoc from Georgia Tech and he said, yeah, Ehsan, like, what is your background? I said, yeah, I know programming, I know quantum, I know biology, but at this point, it seems that I don't know anything. I'm trying to quit the program. And he said, actually, I have a problem that you might be interested to solve. And it wasn't quantum biology. It was quantum machine learning, like machine learning for designing quantum logic gates, which ended up to be a quantum machine learning project. So that morning, he gave me the problem and we could solve that problem in a week. And in 1 month, we could have like the material needed for publications. And we ended up to have a publication in Physical Review Letter, like in a few other journals that you can imagine from physics. And then the whole thing changed just by one conversation in the kitchen. So maybe the story is that you never know what's going to happen and what you never know that what life is going to bring to you in the future. You just have to be patient. So the good part was that I could finish my PhD in 5 years. So I did the whole thing in 2 years and I was out of the university in 5 years. And then I did a postdoctoral program on that topic with Dr. Barry Sanders. And then from there, I joined PointQubit. Like it was 2016 that I joined PointQubit. And since then, I'm working on a mix of classical and quantum machine learning projects. And my main interest is learning theory, like consciousness, where is it coming from? I like to think about these sort of things. And it seems that the quantum machine learning and quantum is the closest topic to this. So if you guys don't have any question till now, which I'm assuming you shouldn't because these are all personal story, kidding, I can start the presentation now.
I've got one. I've got one. So, so you did not finish your PhD?
I did finish the PhD.
You did? Okay.
No, I did finish the PhD like after 5 years. So the whole PhD program took 5 years, but I had to change the whole topic, the whole thesis, and those people who were in my candidacy proposal exam, like they were so surprised that the next year they were seeing the whole different topic. And they said that this is the first time someone doing such thing at university. It seems that I was the first one who was doing that.
Bravo, bravo. Best PhD is a done PhD, of course.
Yeah, it's a done PhD. So yeah.
Cool.
Hey, Ehsan.
Hi.
Hi, my name is Pathikrit Mukherjee. How are you?
I'm doing well. How are you doing?
Good, thank you. So far, so good. I have a quick question. You are saying that you are working on, or actually you started to work on designing quantum logic gates using machine learning, right?
Yes, that is correct.
That's one of the topic I have been searching for, and if Terrell might remember, like in one of the session, I actually brought that up. Like, is there any way to reverse engineer any logic to a quantum logic gate? So even before you start your session, I want to understand if there is any way to do that. And let me ask you if I'm trying to explain you what I'm looking for. So suppose you're given a problem, you're given a logic gate, and the logic gate does not make any sense. But can you reverse engineer it to a certain point where we can say, okay, we put Hadamard gate, we put say other gates, and we can frame a quantum logical infrastructure so that whatever logic gate has been presented to me, it can be represented by that. Is there any law or rule or mechanism of doing that?
Yes, there is one law or mechanism that we can do it, and that is designing the Hamiltonian itself.
Okay.
Because at the end of the day, that unitary operator that corresponds to the underlying Hamiltonian, represented by that quantum system. So one way that I'm aware that people are doing are solving that problem using machine learning is to design the whole Hamiltonian, and it is sort of designing the whole quantum system such that that quantum system, when you evolve it, the final evolution of that quantum system is the unitary operator that you're looking for. And you can guess. So let's say if you have a quantum system, then what are the parameters that you can tune that system? It's usually the frequency of the qubits. Let's imagine you have superconducting qubits. Then each of those, and again, let's narrow down that a bit further. Let's say you have charged qubit. Each of those qubits, they have some frequency of their own. At the end of the day, what you're looking for, you can learn the structure of the frequency of each of those qubits over a certain time, let's say from 0 to 20 nanoseconds. You could use reinforcement learning in order to learn the structure of those pulses in order to evolve the system such that at each step you're getting closer to the gate that you like. And then you know that reinforcement learning has a few components that have to be met so that you can call the whole process a reinforcement learning process. You have to define the reward, you have to define the state of the system. So all those components, you can define those and then assign those to a reinforcement learning algorithm. And at the end of the day, what you're ending up with is a policy representing the pulse. That pulse acts on the qubit. And when you're evolving the system, then you're going to end up with the unitary operator that you're looking for.
Okay, thank you very much for your answer. I mean, I was looking for some sort of hints in this, so it's great that you have done this work. Thank you. Go ahead. I'll not disturb you anymore. Thank you.
No, never. Please, please. If you have any question, just stop me.
Yeah, I think that question and answer was worth the price of admission. That's it for tonight. Then we don't need to do anything else. That was a awesome answer. Thank you.
Yeah, the only thing that really makes me a little bit nervous is like the machine learning is probably the only way of doing that, right? Like, don't we have any other way of like normal electronics, or there is no other way? I can understand that because it requires so much of effort. But if we have machine learning and reinforced machine learning, then it will make our life easier. I agree. But yeah, I mean, machine learning is like it's a different domain altogether. So. Mm-hmm. I mean, yeah.
Yeah, there is one famous way of doing that, because imagine that this whole machine learning got famous in the last few years, like in the last decade. But before that, the main approach was control theory. There is a lot of literature on that side that people in the past, they were using control theory in order to solve this problem. And then you can see the connection. Why reinforcement learning? Because reinforcement learning is sort of, I can call that the brother to the control theory at some point. And that is the closest version of machine learning to solve such problems. So you could always pick up one of the control theory algorithm, like Krotov, that's the famous one that you can choose that people are using in the field. Krotov algorithm or others, like I know grape is another greedy based algorithm that people came up with, and it's very famous in the field. Yeah, there are other ways other than machine learning that you can pick in order to solve such problem.
Okay, thank you.
Cool. Thanks, Ehsan.
Yeah. Okay, so let's let me give you an outline. This is a 3-line outline. I'm sure that you guys have read this so far, so I'm just gonna pass on this. But the longest story short is gonna be quantum, classical machine learning, and quantum machine learning. So you might find this presentation not that much technical, but you can ask me question and take it as much as technical that you like. But I'll try to keep those technical concepts in a very high level, but hopefully if you have question, we can dive into those topics. So why quantum computers? So these are the 3 people that I admire the most when it comes to the computing. So the first person from the left is Moore, and you know the Moore law. The middle one is Feynman, and the right one is Seth Lloyd. Why do I have this picture in here? And I'm sure that you guys all know about the Moore's law, like, and in a sense that it was saying that in every year the number of transistors should be doubled on the classical side of the computing devices. And then as you can see, as we are approaching to the year, like any time after 2004, you see that growth or that rate of increase of number of transistor on the CPU chips decreasing. And one main question was that, okay, what do we do after that? Is this law gonna be broken? And the answer to that question came from Feynman. So in 1982, Feynman posed this conjecture in a sense that a classical Turing machine would experience an exponential slowdown when simulating quantum system, while a universal quantum simulator would not. So the idea is that, okay, so if you are reaching to that plateau, if you cannot increase the number of transistors on the chip, then how about changing your universal computing device? And instead of using a universal classical one, let's use a universal quantum simulator. But this was a conjecture, like it wasn't proven. Feynman just proposed that, okay, you might be able to use such a machine, a universal quantum simulator, in order to resolve that sort of Moore's law break. Then it was 1988, Seth Lloyd prove that conjecture. And what I wrote here is actually the abstract of that paper that Sedloyd published in Science Journal in 1988. And it was important enough for him to just say that the Feynman conjecture that quantum computers can be programmed to simulate any local quantum system is shown to be correct. And this was the start of the whole process of people being interested in quantum computing. So it was 1988, and then maybe one of the first quantum algorithm that got everyone's attention was proposed by Peter Shor in 1994. That was the famous algorithm that if you're given a number, how to factorize that number into its prime factors. Like I know that most of you know that this is an approach that people are using in cybersecurity, cryptography. They just multiply two prime numbers, come up with the bigger number, and then if you can factorize those, then you have broken that encoding procedure. But there's one important thing about Peter Shor algorithm. It is true that his proposed algorithm is exponentially faster than any known classical algorithm. But the important part here is that it doesn't say that this is the only algorithm that can do it. Maybe 1 week from now, some smart people coming up with a classical algorithm that can beat the algorithm that proposed by Peter Shor. There is no theory that can say that no one can come up with a better classical algorithm than the one that proposed by Peter Shor. But at the moment, what we have for factorization, like maybe the best algorithm is the one that is proposed by Peter Shor.
Hey, Ehsan?
Yes.
You know, given your intimacy with quantum computing, do you think that there's not possibly, but do you think there's likely a better Shor's algorithm out there? In other words, a better solution quantum-wise on a quantum computer for the prime factor problem? What's your gut telling you?
To me, that's a yes, because we've seen that over the last year. I'm sure that you guys know Evin Tang. If she continue to do what she's doing now, by the whole path that she's taking, she's trying to de-quantize quantum algorithms. And one of the famous one that she quantized was quantum recommendation algorithm and also quantum clustering algorithm. So in that case, we have seen people come up with some, and the main approach from her work was randomized algebra. The whole process, he replaced the whole quantum information process with a randomized linear algebra, and then she can get to solve those sort of problems, quantum clustering, quantum recommendation system, within the same class of complexity. But here's the thing. Over the years, we've seen many people are coming up, at least they claim that they propose better classical algorithm than quantum one. But the beauty of it is that maybe I see the mission of the quantum computation or quantum information processing in twofold. The first fold is that, okay, by itself, it has to be able to come up with more efficient quantum algorithm to solve classical or quantum problem. The second fold is that it should trigger other people's mind in order to come up with better algorithm than the quantum algorithm itself. So in both cases, you can see progress are happening because of the quantum. Even Tang, when she proposed those two classical methods, even those are coming from the idea of having quantum algorithm in place. So you get the idea from there, and then you transfer those to the classical one. So this is very important. So I'm like, maybe to answer your question, that's a yes, but I'm not worried in a sense that the whole quantum will be replaced by classical if we have every single quantum algorithm replaced by the classical one. Because I'm sure that there's also true on the other side that someone might come up with a better Shor algorithm. So the first one is Gruber's algorithm, 1996. And the idea was that, so classically, if you're given a data set that is not sorted, that data set, and you're looking for one specific item, then on average, you have to look at least, you have to go through at least half of the data set on average to find that target. So what Shor is proposing is that, okay, so let's say you're given such a problem, then I'm going to give you a quadratic speed up over that exponential. Let's say if you're given a data set of like 1,000, then this is going to be a square root of that 1,000. So like this is only quadratic speed up. What I'd like to mention here, this has many implications on many quantum algorithms that exist for optimization. So you often hear about QAOA or other types of quantum optimization algorithm, and you wonder that none of them are guaranteed to give us an exponential speed up for general case of problem. The reason is that the underlying process, the underlying phenomena of those quantum optimization algorithms are attached to Gruber search algorithm. At the end of the day, as you're evolving the system, you're rotating in a Hilbert space such that at the end of the day, after that rotation, that whole evolution make the solution closer to the one that you want. But there's a limit for that speed, and that limit comes from the underlying theory of Gruber algorithm. Since Gruber algorithm gives us only quadratic speed up, in general, when we are talking about quantum optimization, again, in general, for some specific problem, for example, QAOA might give us some exponential speed up. But in general, it is constrained by Gruber search algorithm. The optimality at best is quadratic. And then we can't get better than that. So this is maybe like I was hoping that maybe you guys have heard about Gruber search, but this was the point that I realized after looking into quantum optimization algorithm. Like one research that I was planning to do is coming up with an efficient, and by efficient, I mean as the number of variable grows, the runtime stay, the runtime change in a polynomial time with respect to number of variables. So I was spending some time in order to see if there is any way to come up with the efficient quantum optimization algorithm. And it seems that it's very hard unless someone can come up with a better Gruber search algorithm, in the sense that if it can give us an exponential speed up. So the next algorithm is HHL. So if you read the paper, it claims that it solved a system of linear equation, a linear system of equation, but it's a coupled system of linear equation. So it claims that it solves that problem exponentially faster than the classical one. So I know, like, maybe some of you know, but there are some very strong assumptions when they announce that this algorithm is giving you an exponential speed up. And that assumption is that if you're given that the whole set of equation, then you're able to encode that, the prefactor and coefficient of those equations, you're able to encode those into quantum state efficiently. Then the HHL algorithm is going to act on that input quantum state and it's going to give you a quantum solution. Now, the question is that, okay, if I have a classical system of linear equations, and this method is going to give me a quantum state at the end, how am I going to use that information? In practice, you can't, unless you're not interested in the exact solution, but you're interested in the expected value of some observables. That observable could be energy, it could be momentum, could be anything that you can imagine that has some physical meaning, some Hermitian operator. So there are two disadvantages here that are not mentioned, that actually they are mentioned in the paper. So the first one is that state preparation here assumed to be efficient, but usually the state preparation is not efficient for this class of problem. The second one is that if I'm interested to know the exact solution for that system of linear equations, then this is not the algorithm for me, because at the end of the day, the solution out of this HHL algorithm is a quantum state. And you know that the quantum state is trapped into the quantum computer. So you can't look into that system in order to see that quantum system unless you do an exponential number of measurements in order to get the full information about that quantum state, which we are not interested. So this was the story about HHL. When I go to the QML part, I'll mention those algorithms that are using HHL based, or those that are based on Groover or Shor algorithm. And then you can, when it goes to that, then you can imagine that, okay, why am I expecting a quadratic speedup? Why am I expecting exponential speedup from that class of quantum machine learning algorithm? So in industry-wise, quantum has many applications. Like I wasn't able to bring all of them here, but you can imagine like quantum finance, chemistry, and even quantum machine learning. I would say like quantum has application in quantum machine learning, and quantum machine learning has application in all the other industries. But let's for now focus on quantum machine learning. And before that, I have a few slides, like 4 or 5 slides regarding the classical machine learning that I like to show. Okay, so I'm usually obsessed with the definition because the way that I was trained in school was, I think I spent 6 months to just learn how to write a problem statement for a problem. And it took me a long time to realize that the problem statement should not involve the solution. You should not refer to the solution when you're proposing the problem there. So learning is any process by which a system improves performance from the experience. So this is a definition by Simon, who won the Turing Award, and he's a Nobel laureate. And machine learning is concerned with computer programs that automatically improve their performance through experience. So what, like if someone, it's very obvious that by learning, we need that any process that improves by experience, so that machine, that person, that object learns. And the machine learning, yeah, like you're, in a simple word, you're trying to make computers smart or learn from the experience. We have different class for machine learning, like supervised, unsupervised, reinforcement learning. So I have one example for each of this. So let's say in the case of supervised learning, you're learning something while someone else is supervising you. And that means that you're trying to learn a function from one space to another. But in that process, you have some extra information, which are the label or the target or the value of those data. And one example is the regression task. From here, given the information of 1 to 4, then you can imagine that, okay, so I can guess what would the answer for the third bird, like what would be the state of the third one. And we have unsupervised learning. So in this case, you're given everything, and you're trying to come up with a solution that really depends how you see that data. So in that sense, unsupervised learning is the hardest thing to do. One example would be if you're trying to do clustering, if I pick one algorithm, it's going to give me 5 clusters. If I pick another one, it's going to give me another maybe 6 or 4. Or even if it gives me 5 clusters, it might assign some of those members to a different cluster which was different from the original one that I was using. So it gets harder from supervised to unsupervised when we are trying to solve a problem, because of the fact that in this case, we're not given that sort of extra information, labels or target. So everything depends on us, and it really depends how we define that word when it comes to clustering or when it comes to unsupervised learning. And one example is here, that given all these round objects, you're trying to figure out that which one is a ball and which one is a fruit. And maybe the ultimate, I think the ultimate goal in machine learning is to come out with a way of doing reinforcement learning in a faster way, because we human, like it takes few months at least or few years for us in order to learn how to walk. But the idea is that can we make objects to learn that part faster? This is a simple example. And it works based on the reward and punishment, in a sense that in reinforcement learning, you let the object start to interact with the environment. And then for those, based on the interaction with the environment, if that was a plausible action from the agent, then you give the agent some reward, and then you promote those sort of action through the experience that, through that interaction that agent has with the environment. And then you're demoting those sort of behaviors that are not interesting to you by punishing those. So this is the base idea. The whole idea is coming from psychology. Sutton was like, who's in, I think he's in University of Alberta now. He's the father of reinforcement learning, he was basically one of the people who came up with this whole sort of let's use reinforcement learning, and let's spend more time on this one. But this was the classical machine learning. But let's go to quantum machine learning. So the idea the problem was that how can we make computers faster? So this is the problem that we really like to solve. And the goal is, like when we are trying to make computer faster, like here, I like to go a bit more into detail. When we are talking about making computer to learn better, that means that we as human, when we are looking at the object, there are some specific sort of encoding in our brain that transform that picture into some encoding pattern that we can, like our brain can understand. So the idea here, the goal would be, okay, coming up with a better representation or with a better way of encoding data into some complex representation. One example is neural networks, that by changing the layers, the nodes or the structure of the network, you're basically changing the encoding pattern of data into a different layer of that network. And of course, there are challenges and opportunity. The challenge is that no free lunch theorem, in a sense that, okay, so if you're given a machine learning task, then you can never say that I'm gonna pick algorithm A and then I'm good with that, I'm gonna stick with that because that's the best algorithm that's gonna work for this case. In reality, you have to try many algorithms, as many as you can, to come up with the best one. And the other problem is the data size is immense, and it's better to come up with those algorithms that they don't need that much data in order to learn. And the question is that, can quantum computers help? So here I've chosen 2 quantum algorithms that, like, among all of this, I haven't worked with tensor networks. I've been working closely on variational circuits, a quantum neural network, kernel methods, Boltzmann machines, and variational circuits. I haven't worked on tensor network, but they are quantum tensor network. They're powerful, and there's some tools that, and many people are working on those. But I picked the first 2 example, and I decided that, okay, let's go into the detail of those 2 quantum algorithms. But before me explaining this slide, one thing that I like to say is that often you hear in many talks in from industry or academic, that they claim that, okay, so quantum is going to change artificial intelligence. There is a very big if attached to that statement that you often don't hear. And it really hurt us, and that is the main reason that we're not very explicit about that statement. And that is the fact that, okay, so if you go back to that no free lunch theorem, what I said was that if you have a problem, then you have to try all sort of tools at your exposure in order to solve that problem. It doesn't matter if that tool is quantum, classical, or any combination of these 2. So the same applies to the quantum. There are two types of benefits from quantum in quantum machine learning. The first one is the speed up in terms of how fast you can run that algorithm. So one example can be, if you design a quantum support vector machine, which is proposed by Seth Lloyd and I think Ali Mohseni and someone else. So if you take that algorithm is faster than the classical SVM. So far so good. So we're not talking about better learning. We're talking about replacing the classical support vector machine with the quantum support vector machine. So far so good. But if you read the paper, that paper never claims that this is a better algorithm in terms of the quality of the learned model at the end. So you see here, so quantum helps with the speed up. So this would also go for quantum neural network. So if you use quantum for training quantum neural network, so you're going to get that speed up. But this is not enough. This is not what quantum artificial intelligence is looking for. What we are looking for is we care about those models that are fast and they perform better in terms of the learning learning performance that we have in mind. And that is a problem. That is the biggest problem that is faced by quantum machine learning. That is called the benchmarking problem. Whatever quantum algorithm, quantum machine learning algorithm that you've seen so far, none of them have benchmarked on the real quantum device, except a few. But what I'm saying is that none of them are benchmarked on a quantum device that is not doable to simulate that on the classical device. Like whatever you've seen out there, like even the recent paper from Aram Haro, I think that famous paper that got published in Nature, even that one, they pick a very simple data set, and they show that, okay, so if you use a quantum device, it's going to give you 100% accuracy, but if you use a classical machine learning algorithm, that's going to give you 100% accuracy. So I'm not saying that those sort of works are useless. What I'm trying to say is that you have to wait, because these are the proof of principle from those algorithms. They're not trying to show quantum supremacy at this point because we don't have a device to show such thing. In order to really show the advantage of quantum machine learning, you need to have a real quantum device, a working version of quantum device. You need to have a data set. Then you pick your quantum algorithm. You run that quantum algorithm on that data set or machine learning problem. Let's say you have 95% accuracy for that model. Then the task is not over because you haven't shown anything, any advantage. Then you have to go to the classical side. You have to pick whatever resource on the classical side that you have, try to solve the same problem, and at the end of the day, if you see improvement from the quantum, then you can announce that, okay, I've seen some quantum supremacy in this case, and you can't even call that quantum supremacy because maybe tomorrow someone can tune the classical one and get a better result. So it's going to be very tricky for quantum machine learning in order to show its advantage over the classical machine learning, at least in theory. But we have to wait till we get a real device. Okay, I think I took too much time on that point, but like to me, it's a very important point that it has to be conveyed to people who are interested to move in quantum machine learning research. Okay, so I picked an example for quantum neural network. On the right side, I try to have a classical neural network architecture, and on the left side it's going to be quantum, and I build up on these two just to show how a quantum neural network would look like. So on the right side, I'm hoping that you're familiar with classical machine learning, but if not, I'll try to explain. So on the right side you have the nodes of the quantum, the nodes of the classical neural network. So the I1, I2, they're accepting the information. They're usually referred to as input layer. We have hidden layer, N1, N2, N3, and we have the output layer, O1. And then the goal is that you're sending your input, picture, data, like whatever input type that you have, you're passing that through the input, and then I'll explain what's going to happen with that input in a moment. On the left side, we have the quantum neural network, and at this point, qubits, each line in here, which in literature you see them, they're calling them wire. Each wire, blue wire here, it's called a qubit. That represent the nodes in the classical case. So let's take again the classical case on the right side. What's going to happen is that we are connecting the nodes, input, hidden, output, through some weights, which we call them learning parameter. And what's going to happen at the end, omega 1 to omega 9, those are the learning parameters that are going to be updated so that we can come up with some estimator, like a classifier from that classical neural network. On the left side, the job of those weights are going to be done by some quantum logic gate. So each of these blocks here, the orange block, they are representing one of the quantum logic gate, and R here refers to the rotation. Like if you guys have heard about X, Y, Z Pauli operator, then you should be familiar with the rotation X, rotation Y, rotation Z, which is basically given the blockosphere, you're assuming that the qubit rotates around the X, around the Y, around the Z. So that in that case, those omega refers to the rotation of each of those Pauli operator, the rotation of your qubit in that blockosphere. So in this case, let's assume that I picked rotation X. Let's say this is R, which refers to the Pauli X rotation, and each of those omega are referring to the angle that each of those qubits are rotating around the X axis. At the end of the day, what I'm looking for, I like to limit my qubits, 2 qubits that I have in here. I like to limit my qubit to rotate in some combination of omega 1 till omega 8 rotation angles. So this is a parameter that I'm trying to learn physically. But you know that, like, if I go one step back, you see here that in the quantum case, it's not complex. You have 2 qubits. They don't even care about each other because they're not connected to each other. So you have a very simple quantum circuit. And on the right side, if you just have some nodes and then you're connecting them with some weights, then basically you're just doing some linear transformation on the input data. So it's not interesting. So in the classical case, what people do is they are introducing some activation function on each of those nodes. That makes the whole process nonlinear, and that makes neural network very powerful. On the left side, we're using entanglement. Like what I've added in here, those are called 2-qubit entangling gates. And depending, like that, solid black circle, that is called the control qubit, and the operation, the plus operation, is actually the not operation, in a sense that if my Q1 is at the state 1, then when I reach to the first 2-qubit entangling gate, then that not operator is going to act on Q2, and then it's going to flip the state of Q2. But forget about how they're going to act. What happened in here is that if you have a circuit, a quantum circuit, that you only have single qubit gates, then you can always simulate those sort of circuits using a classical device. There is no benefit. If you don't have 2-qubit entangling gate, then you don't need a quantum device in order to perform that sort of simulation, because a classical device can do that efficiently. Those sort of 2-qubit entangling gates, they're making the whole process more complex, in a sense that it gives the network or quantum neural network more power in order to learn the learning task that you're looking for. Okay, let's pick an example. Let's say what I'm interested is a classification of 2 classes, orange versus green. So in classically what we do, we pick one of those samples, let's say one of the orange one, and then in this case, we have them in 2 dimensions. So I take the first dimension and feed it into I1. I take the second dimension, feed it into I2. I pass it along the network, and then that network is going to do some nonlinear operation on the input qubit, on the input data. And O1 is going to represent some number, which I'll explain how the learning process is going to proceed. But what I explained was the forward propagation in the classical neural network. On the left side, what you have is that you're encoding your information, again, picking that orange one, you're encoding your information each into 2 qubit. One important thing here is that you hear that quantum mechanics is linear. It is true that it is linear because the wave function in Schrodinger equation undergoes under some linear operator. So if we claim that quantum mechanics is linear, then why do we expect nonlinearity from this sort of circuit? The reason is that those qubits that we are encoding the information into, we are not actually, the way that we are encoding the information into those qubits is actually into the phase or the rotation angle of those 2 qubits. And rotation is some cosine and sine. And then because of those cosine and sine, when you're evolving the system, at the end of the day, you have those operators acting on those values x1 and x2, and then that gives the nonlinearity. But let's assume that you picked one of those samples, you encoded those samples into 2 qubits separately, and then you're evolving that whole information through the quantum circuit. And at the end of the day, on the classical side, as I said, you have an O1, which is the output, which is going to represent some function that depends on x1, x2, which is the 2 dimension that our data exists, and omega, which are the parameter that we're trying to learn. On the left side, we have the same thing. We're doing some measurement on each of those qubits, and then the result of the measurement is going to be a single number, like one real valued number. And then in order to make this whole process into a learning process, we are continuing by picking each of those points, green or orange, we're picking those, encoding those into the either classical or quantum. And then after we pass the whole points, then on the classical one, we do some back propagation. On the quantum side, we do, again, we do some back propagation in the sense that we update the weights or the angle, rotation angle, by taking the derivative of f with respect to those angles. And then we are updating those learning parameters. If we continue this enough through some certain number of iteration, then we'll see that, okay, so at the end of the day, on the classical one, I have a set of omega that if I stick to those omega, which we call them optimal learning parameter, then I can have, let's say in this example, I have a perfect accuracy for classification. The same thing on the quantum side. If I stick to those omega that I've learned through this whole learning process, then I have a model that can classify this sort of classification task with the highest accuracy, which is 100%. So this idea, this simple idea, you can take this and you can generalize this to any sort of quantum neural network. Like you could replace this with CNN, like quantum convolutional neural network, quantum, those recurrent neural network, different type of quantum neural network that you can consider in order to come up with a quantum neural network model. You might say, okay, I won't care about the quantum one because I could simulate this on a classical one efficiently. But as a matter of fact, if you choose the configuration, the way that you put your single qubit and 2 qubit, if you choose them wisely, then there is no classical device which can simulate the quantum evolution of your quantum neural network. This is maybe the main advantage of using quantum neural network, because you get far better complexity from a quantum neural network than the classical one. So this is very important, and this goes back to the advantage of speed. So quantum neural networks are faster for some specific way of arranging those single and 2 qubit gates into the quantum neural network. So if you guys don't have any question, I'll move on to the next one, which is quantum kernel machines.
Yeah, let me ask one if I may, just to give you a break too. So the weights, so you're entangling the 2 qubits and you're doing the phase rotations for each of the weights in there. So all 8 weights, or maybe 9. And so that's just moving the tensor around a bit. And then the outcome would be some state. And then that state gets fed back to the classical computer.
Yeah.
What am I missing?
No, that is correct. Like that state, I think you're right. Data state, okay. So the output of that quantum neural network is a quantum state. That f, which is the function, is just a single number. It's not like the quantum state is already vanished at that point, in a sense that f itself is the expected value of some operator under the quantum state that came out of that quantum neural network. So at that point, you're not dealing with the quantum state. You're just dealing with the expected value of some operator, which I call that f x1, x2, omega. Then you're right. At that point, that shouldn't go to that bug. That actually, following, if you see the path of the update path. So what I meant is that those omega gets updated. And then in the next round, when you're picking the second point, let's say the second orange, in the next round, you have updated the weights, omega 1, omega 8. plus you take the second point, you feed it into the network. Again, you do the measurement. Get fx1, x2 omega for the new points. Then you do this process for all number of data points that we have. Let's say the batch size here is 1. Batch size, I mean, like at each iteration, you just take one single sample, pass it through the network. Mm-hmm. Sorry, maybe this plot is a bit confusing, but forget about the part that the output of the quantum network goes to the, it does goes to the classical device just to update the weights of the quantum neural networks. Because in there, you're using some classical optimization process in order to update those. So one thing that is important, and I didn't bring that much detail in here, but in the quantum case, when you're trying to get the, let's say, get the derivative of f with respect to omega 3, then it's gonna, that derivative itself, that corresponds to another quantum circuit, which is equivalent to the derivative of this whole original quantum circuit with respect to omega 3. So you're going to have another quantum circuit, and then you're going to do some measurement on that in order to get the derivative of f with respect to omega 3. So you have to do these number of measurements. Like for each of course, the classical one, the classical device is going to give us the updated omega. Let's use the simplest optimization algorithm that we have. Gradient descent. Then in that case, given the initial omega 1 to omega 8, you need the derivative of f with respect to each of those omega. So for each derivative, you have a quantum circuit. You design that on a quantum computer to get the derivative, and then you're passing the derivative plus the original weights in order to update the new weights. And then you have the new weights, you pick the second sample, pass it through the network. You do this process enough in order to reach some sort of convergence.
Okay, gave me enough to chew on there. The gradient descent clue was helpful in helping me understand it. Thanks.
Okay, great.
Hey, Ehsan, this is Pathikrit again. So you are I mean, in normal neural network world, right? Suppose we are trying to train a soccer ball or a watermelon, as in your picture. We try to convert the picture of the ball into bits, right? Like in the world of matrices. And we try to create, we try to find out the, you know, the pixels and try to give a bit and then convert it to a matrix, and then we start the iteration in normal, in the classical neural network. How do you start this neural network from the right initialization? Like, do you apply any Fourier transformation or something on the initial values of the pixel bit that you got, or how do you start it? I understand that once you start it, it can do the iteration. You update the network. You get the optimized weight function. You do a forward and backward propagation, both those things. But how do you start it?
Okay.
How do you get the input from?
Yeah, like your question goes back to the classical or the quantum one?
The classical, the quantum part. Yeah. How do you start the first quantum? How do you generate that actually?
Yeah.
Out of the, yeah.
Let's say, let's pick an example. Let's take an example of maybe grayscale picture, like any picture,
right.
Dog grayscale picture. If I take one of those picture, then in reality, what I can do, each of those pixels is a number between, I guess it's between 0 and 256.
Right,
like
you're right. Yeah, that's how it is. Yes, 1 to 255, I guess. Yeah, 0 to 255.
Yeah, 0 to 255.
Yep.
Then let's say I have 8 by, like my resolution is 8 by 8. So that means that I'm gonna have an 8 by 8 matrix. Each has a number between 0 and 255.
Right.
Now, in the classical case, the first thing I do, I'm flattening this matrix. I'm turning this matrix into a vector. So now
Right.
I'm going to have one single vector of 8 by 8, which is 1 times 64 elements.
That's right.
Okay. Again, on the classical side, if I try to solve this problem using the classical neural network, the input layer needs to have 64 input nodes. So each
That
of
is
those.
correct.
Okay. So now let's take this example into quantum neural network. So let's say in that case, I'm going to have a quantum neural network with 64 qubits. And the initial states, each of those blue qubits that you see in here, each of these blue qubits, what I can do is that I'm going to take the real number, the first number in that 164 elements that I have. I'm going to take the first number, which is a float number, and I'm going to replace one of the rotation angles, psi or phi, one of these with that number in order to initialize the first qubit with the information of the first element of that 1 times 64 dimensional vector. I do the same thing with the rest of those elements. I pick another 63 qubit and encode each of those information simply into those qubits. Now I have initialized that picture into some representation, some quantum representation or quantum state.
Okay, okay. So you're basically transforming a real number to probably a complex number kind of form, right?
You don't even, no. You don't even have to. I know what you're referring to. You're referring to the fact that the psi itself lives in a complex Hilbert space. That is true. But when I'm picking, but the angle of those, you see the psi or phi, the angles, those are real numbers. So I'm not changing the value here, the real number here into complex number. When I replace those angles with these real number, after I initialize the quantum circuit, then you are right. Then that is what's going to happen intrinsically into that because of the quantum state. Like when I encoded those information, I encoded in a way that I pick the real number and I replace the angle in that qubit with that real number. But when I generate the quantum state, that quantum state is going to be the coefficient of those states is going to be some complex number. In some sense, you're right. We are changing, we're moving from real space to the complex space.
Right, right. That's what it looks like. Okay. Yeah, I mean, in one of the conversations that I had, they were trying to say that in some cases they apply Fourier transformation also to convert to wave function, and then from that you can feed that wave function into the quantum circuit so that it generates some value.
Yeah, like even like in both cases, because one thing that is known is that neural network cannot give you the Fourier transform feature of the actual data. It is always nice to have it extracted prior and then provide that extra information to either classical or quantum one, but it's not necessary for the encoding. But it is always useful if you think there are some features like periodic features that are going to be useful from that sort of Fourier transformation.
Okay, thank you.
You're welcome. Okay, so the second topic is quantum kernel machines. So the idea of the kernel machine is pretty simple in a sense that, let's say you're given a data set, which is on the left side, which as you can see, those points, they're not linearly separable. You need a nonlinear classifier in order to separate green from the orange dots. So here's the idea. The first step would be, okay, let's pick some explicit feature map in a sense that we call phi here a function that you can apply on each of these points and then take them from these two-dimensional space which is the original space of the data point, into the higher dimensional space, which is, in this case, 3-dimensional space. So what's going to happen is that for some sort of those feature map that you apply on these original data, you'll see that those points are becoming linearly separable in higher dimension. So using some hyperplane, you can separate those two classes of orange and green. So there's one problem here. In practice, when you want to do this sort of transformation, in practice, you have to go to the very high dimensional space. Sometimes like a million or like a hundred of millions dimensional space in order to see that sort of linear separability between those two classes or multiple classes. This is where the kernel machines comes to the rescue. And what they say is that, okay, if you have a kernel machine, what I care is only the overlap. Like, let's take the transform data in the new space. It only cares about the overlap of these transformed points in the new space, the overlap of each data sample with the other one, in a sense that, okay, so take this example. Let's say I have a 2-dimensional database, and I would say, okay, so if I choose a feature map that I could go to a 1,000,000-dimensional space, then I'm going to use a machine learning algorithm, a linear one, in order to separate those two data. Great, awesome, let's do that. But if I go from 2-dimensional space to 100 million dimensional space to get that sort of performance, someone might say, okay, this is a very high dimensional space. Is there any way that we can still use this sort of property, but not going explicitly into that high dimensional space? The answer is yes, you could. You could use kernel machines. And what kernel cares about is a function, just a single function that represents some similarity between those 2 points in the feature space. And by feature space, in the transform space that you're dealing with. An example would be, let's take an example of 2 ball here. If you're using a kernel machine, then the idea is to have a kernel or pick a kernel. Like one famous one is RBF kernel in support vector machine, or linear kernel or polynomial kernel. So the idea would be pick a kernel that for those objects that are similar, you have a high value for that kernel. And for those objects that are not similar to each other, the kernel can distinguish that, okay, so these 2 objects are not similar, so I have to assign a small similarity measure between these 2 objects. So this is sort of a classical representation of kernel. The fastest way that, I don't know if it was clear, but if you guys have any question, I can clear that. So the idea is that, okay, now that you had that sort of information, you've chosen the right kernel, then the idea would be, given new samples, can your kernel decide that whether 2 objects are similar or they're not similar to each other? Okay, let's make this quantum. In the quantum case, like the quantum kernel machines, the first thing that we have to do, we have to come up with a kernel matrix. And each element of that matrix is actually representing the similarity between 2 elements of that data set. So the idea is that you have a classical computer, and you have to, like one thing you need to do, you have a classical computer, and you have a matrix there. That matrix is called kernel. And then you want to use the quantum circuit in order to get the similarity between each pair of that data set and write it into that matrix. So what we do is that, okay, let's pick 2 pictures. Let's take a watermelon and a basketball. And let's take a quantum neural network as an example here. The quantum circuit here. So you have to encode the information of each of these 2 objects into the quantum circuit. And this is how we do it. So the idea here is that if you look at the orange one and the green boxes in here, the idea here is that every single element, you see we have the same number of C0 gates. They have to be the same. We have the same number of X gate. We have the same number of Y gate. Like everything is stay the same except the information of each object that you're trying to get the similarity between. So this is the only part. So in another way, you have a function that represent each of these blocks, like orange one or the green one. And then that function takes different sort of input, which is either X1 or X2. X1 referred to the basketball, X2 referred to the watermelon. And by doing measurement at the end of this evolution, you're gonna get some similarity between these two objects. You might say, okay, so why not stick to RBF because it does the same thing, or any other nonlinear kernel that I can do classically. So it is shown that these sort of tasks you cannot do efficiently using a classical device. There are some kernels, like quantum kernels, that if you wisely choose your single qubit gate and 2 qubit gates, if you choose them wisely, the combination of these two, then you are guaranteed that that sort of similarity measure that is coming out from the quantum kernel machine, you can never reach using a classical device. So let's say in this case, we do this and we realize that, okay, great, the overlap is very small, and then the kernel that you have chosen, again, the kernel is coming from the way that you have put those single and 2 qubit gates together. You might ask, okay, how do I know it's the best sort of kernel that I can imagine? There are different ways of picking up the right configuration for those gates. Like one would be turning this whole thing into some adaptable approach, like introducing some learning parameter on each side on orange and green, and update those parameters with respect to some performance measure. Or the other way would be you could use reinforcement learning to come up with the best setting of these gates in order to come up with the best similarity measure out of this quantum circuit. So in this case, what you can see here is that there are so many work on quantum kernel machines, but the basic idea is that you have to come up with quantum circuit in order to encode each of those objects into that. Then after that, you have the kernel matrix, and then you can send that kernel matrix into SVM, into any classical kernel-based machine learning algorithm in order to do that classification. But the main idea would be the element or the similarity measure is coming from a quantum device. So this is one table. I picked this table from Peter Widdick book. Unfortunately, he's not with us anymore. But yeah, this is one of the tables I really like, and he actually categorized. Although the book is pretty old, with the current speed of progress within the field. But you can see here, for example, the K-median algorithm, since it's using a Gruber-based algorithm, then the speed up is going to be quadratic because the Gruber itself is a quadratic, it's going to give us a quadratic speed up. So it's also the case for, let's take another example of, yeah, like nearest neighbor, again, Gruber, yes, then the speed up is quadratic. Let's take an example which is principal, yeah, like principal components. Again, the principal components analysis, it is sort of using the quantum phase estimation or Shor algorithm, and that gives us exponential speed up. There's an assumption there that you can prepare this state efficiently. That's why you're getting that exponential speed up. But maybe the message that I had was that usually when your quantum algorithm depends on the Groover one, your quantum machine learning depends on the Groover one, then it's going to be a quadratic speed up. And if it depends on phase estimation, quantum Shor algorithm, those sort of algorithm, or HHL, which by itself, again, it depends on the quantum phase estimation and Shor algorithm, then you're going to see some exponential speed up. Okay, I think by that slide, I reached to the end of this presentation. This is the team that I'm working at 1QBit with. As you can imagine, we are like right now, like the first person joined us a week ago, so I haven't updated this slide. But we are a pretty small team at 1QBit, like just 5 of us that are working on quantum machine learning. But there's a huge branch at 1QBit. If you guys like, I can talk about 1QBit itself too. Like, what are the different departments that are working on quantum? We also work on non-quantum machine learning optimization. There's a variety of different topics that we work on. Yeah, by this is the last slide. Thank you so much for your attention. If you have any question, I'm here to answer those questions.
Thank you, Ehsan. It's great. It's actually understandable to a degree, and I really appreciate that. A lot of times, particularly with machine learning topics, they're just so intense that you know, I walk away just more confused than when I started. So you've really brought it down to a level that's quite understandable and much appreciated for doing that. That's awesome. Any questions for Ehsan?
Yes, hi, Ehsan. It's David Garvin here. Thanks very much for that talk. It was very interesting. Can you go back just one slide to the table that you were showing, please? Thanks. So when I look at that table, it concerns me from the point of view, and I think this is one of the points you were trying to make, that anything better than the quadratic speed up as in the exponential one, which then means you're not using Grover, you usually end up using HHL techniques, but ultimately in the quantum data column there, it always says yes. So then you end up still having this problem of loading the data into your quantum state, which potentially is exponential. And so to get the exponential speed up, you have the slow data load. And like on that table, I don't see any cases where that doesn't happen. And that's the frustrating thing so far with QML.
I do agree, but I think the most frustrating thing with QML is that even this is one of the reasons that you don't see many companies or universities to invest too much on this, because at this point there is no hardware. Like maybe you could use some sort of hybrid technique in, like, for finance or chemistry. I think quantum chemistry is one of the most promising one that people might see some change in the future. But when it comes to QML, we need a real device, and we need to be able to do a meaningful benchmarking procedure. And the other thing is that if we try to, maybe if I can make this part, this is my personal understanding of QML. The real advantage of QML would be on quantum data, not necessarily on the classical data. And by quantum data, I mean is that, let's say if you are going for quantum phase detection, or quantum, or even in quantum chemistry where you're dealing with quantum state, or you want to classify quantum states. The input to the network is a real quantum state. Or you want to use QML for solving, like the same way people are using classical ML for solving quantum chemistry, coming up with the ground state of the energy of molecule. The advantage of QML would be more highlighted or like more clear when it comes to dealing with quantum problems, not necessarily classification of classical images, or having a quantum support vector machine. Like this is my, I think what I see that this is my personal impression from QML. And for that reason, what I'm interested is mostly toward application of QML on quantum system, not necessarily on the classical.
Yes, I think that makes sense. So as you say, the good use cases are where you applying machine learning or quantum machine learning to a quantum state that's an input. In other words, it already has come from some other quantum computing process. And then preferably you also want the output to be like a single number or two numbers or something like that, as opposed to the whole state. So you want to be able to apply that operator to collapse the output to a small number of variables. And that makes it harder to find the use cases, but it also at least focuses you on the space of use cases to look at more precisely.
Yeah, that is true, David. It's very challenging to come up with the best use case here.
And as you say, we need more qubits and less errors.
Yeah, I think that is one thing that we all agree on, and like hopefully that's gonna happen in at least my lifetime.
Yes, I'm hoping that too. And I hope it's in the near term of your lifetime.
It's got to be a little frustrating, Ehsan, that, you know, I recall back in the early days when we had punch cards and that sort of thing, you know, you'd get the supervised learning, you'd submit your deck overnight, and the next day you would at least get an answer. And, you know, you go from there. It was slow compared to today, you know, with classical computing, compiling and all that stuff is just a non-event. But man, you're developing this code here in a sense, figuratively, and my God, you can't even run it. Like, not even tonight. I mean, you got a couple years to wait. That's got to be, that would drive me crazy. How do you keep going?
Yeah, like
seriously.
I think the theory side is still interesting. The part that you at least prove that there's a speed up for some of those algorithms, like even if you can't run those algorithms. I think that's the only part that keeps me alive in this field. Otherwise, with not having the device, it will be hard to keep going. But as David said, we are hopeful that someday we're going to have a quantum device.
But I might say, you know, it does make you sharper and you think through things. Like, and I know it's a trivial example, but it is an example. You know, when we used to punch cards, we thought about everything very deeply, you know, before you know, actually taking the code and putting it into cards and running it overnight. And now, you know, now that I have that turnaround constantly, you know, with classical code, I don't really think that much. I just, oh yeah, maybe this, boom, it worked, okay, I move on. And so, you know, there's a lot of benefit to having some, you know, slowed down feedback loop or something, but you've got none. You know, you know. I admire that. That's a tough call. Anybody else? Any comments before we end here this evening or this? It's still afternoon for Ehsan. You still got several hours worth of stuff to do today.
Yes, it is 5:30 my time, and I think it's 8:30 your time, right? It's almost night time.
Yeah. Are you a night worker or a day worker? When do you do your best thinking?
I usually start at 9 a.m. till 1 a.m.
To 1 a.m.
Yeah, I don't know if this is night or day, but I can't work early morning.
I hear you. Yeah, your mind's clear.
I know Einstein, he was sleeping a lot. Even Feynman, but he was so lazy that he was missing most of the morning classes. And there was so many complaints about him that, yeah, he's not showing up in the early morning classes. And then for that reason, he was having most of his classes in the afternoon. Yeah,
I wasn't aware of that.
Yeah, it's very common. Like when you go to grad school, like I think any science grad school, you don't see anyone early morning except the profs. They're always early. I don't know how they can make it, but if you're a student or postdoc, I haven't seen many early bird people.
Yeah, when I did my PhD, I guess I was in my 40s, late 40s. And I was early morning, and the rest of the dudes and dudettes wouldn't even begin to thinking of showing up until around 11 a.m. But they were there till 4 a.m.
Yeah, that's the thing. That's the thing. Yeah, I do sleep a lot. I think that's a problem with me. Like I'm usually sleeping 8 or 9 hours a day. So.
Anybody else? Comments? Questions?
Hey, Ehsan, this is Pathikrit again. Thank you very much for your presentation. It actually opened a lot of doubts and questions that I had in my mind. So it gave me a very good understanding about how to start. In future, if I want to ask you for some help, how do I get to you? Like, is LinkedIn or an email or some sort of thing, like for further future, some document, some artifacts or documents or some theories, whatever, like the reinforcement learning algorithm that you said about, the quantum logic gates, all those things. How do I reach you?
LinkedIn would be the best. I'm very responsive on LinkedIn.
Okay, thank you. Thank you. I'll send you a request then.
Okay.
Connection request. Okay, thank you very much.
Cool.
Great. I'm glad you find this useful.
Got a quiet group here tonight. I think you really got us thinking instead of talking. So anyway, let's end here then. Thank you very much, Ehsan. Appreciate it. Really, really enjoyed your visit and learned quite a bit. I must say, you kept it simple enough that we could walk away, I think, with a pretty good understanding. But definitely hungry for more, I must say.
Great.
So thanks a lot.
Same here.
Oh, sorry. Can I ask maybe one more question then?
Yes, go ahead, please, Dave.
So one of the topics you didn't talk about was the bottom item on your list of different QML, which I think was the variational circuit. So to me, I think that may be one with a lot of potential in the near term, just because by definition it kind of will run on the NISC devices. What's your thinking on that?
I do agree with you in a sense that like even in that sense, quantum neural network is a subset of variational quantum algorithm. And as you said, they are very famous. I think they are the frontliner of having quantum supremacy in the future, in a sense that many quantum chemistry algorithms, the one that are using quantum eigenvalue solver, like variational eigenvalue solver, they're using this sort of variational technique in order to find the ground state of those compound molecular atoms. Yeah, I do agree with you. Like that is one of the, I think that is the most active field currently, and the most hopeful one in the future.
Yeah, and as you say, I mean, it actually looks quite similar to what you did talk about in the QNN.
Yeah, that is true. And the other thing, like about this call, I know like I kept it very high level, but in the future we do have some, like we still do some publication at 1QBit. Like maybe in the future, if you guys were interested, we can also talk about giving more technical presentation on those topics. But again, it really depends on the interest, and like I was like my concern was that it could become very technical, because I'm the person, I'm not usually learning from lectures. Like I'm usually lost after the 5th or 6th slide as soon as the first equation shows up. So I'm like 100% lost. So I'm usually, whenever I go to a workshop or conference, I'm avoiding that topic unless I've read that work and I have question about that work that they've done. Otherwise, I don't think, I'm not that smart to just look at these slides and then figure out what they've done. So I was trying to avoid that, and I prefer, like whenever I give a technical talk, then that should be targeted toward a technical audience, and at least those people like spend some time of their life on that topic. Otherwise, it's gonna be a boring one for the audience and for the speaker both.
Well, I'll say if you ever want to come back and talk as technical as you want, you're more than welcome to do that, because we pretty much self-select. So if you feel like talking tech sometime, let us know, and we'll let other people know that it's going to be highly technical, and you'll get the people that you'd want, I think.
Awesome.
So,
great.
Yeah, seriously. Another, actually, a really good group to talk with. These are is the New York Quantum Computing Meetup group. That is a very sophisticated audience there. So if you'd like to give that, it's the Wall Street folks and all that. If you want to give a talk there anytime, let me know and I'll get you set up with Steve Willis, because you'd probably get a lot out of it as well, because the audience is at a very, very high caliber.
Sure. Yeah. Like even for this audience, because I'm not sure. This was my first time giving talk at any meetup group, so I wasn't sure what's the back. Maybe the current background of this audience is good enough. Yeah, we can try even this audience at some point. Like try more technical one. If there was any interest, like please let me know if there was any interest, so I can prepare a technical talk in the future.
Oh, dude, there's interest, especially in the machine learning, the QML space. Absolutely. I don't understand a word of it at this point. I mean, today was perfect for me, but certainly guys, David and others obviously would probably really appreciate some dialogue with you.
Okay.
At a really high level. Yeah. So whenever you want, you just say the word, we'll get you set up.
Awesome.
It'd be our pleasure.
Thank you so much for the
Seriously.
opportunity again.
Yeah. You got a thumbs up already, even before we asked for the thumbs up. There you go.
Okay, great.
Thanks a lot, man. Appreciate it. Everybody, thanks for the questions too. And we'll see you again I guess there's something tomorrow, but it's a much lower level talk. So have a good night, everybody.
Have a good night.
Thanks a lot, Ehsan. It was great having you. Really good.
Thank you.
Thank you, everyone.
Thanks, Daryl. Thanks, Ehsan.
Sure.
Bye.
Yo, bye.
Hey, Daryl, is there any way I can find that New York Quantum Group in Meetup? I think you're on mute.
Yeah. Go to the Meetup meetup.com and search for it, or go to the Quantumapalooza site. And for some reason, he didn't have a meeting this month, but it's you look on the past events, and usually it's the last Tuesday of each month. Just take a look at the last events for the end of May, and so there'll be a link to his event, and that'll take you to the Meetup site for sure.
Okay, thank you very much.
Yeah, they have, I don't know why he didn't have one this month, but yeah, that's a very sophisticated crowd. That's all the Wall Street folks and such. Yeah, so he's got really high level talks. Anyway.
Thanks.
See you all later. Sure. See you all later.